Oh yeah, please turn in your quiz. I could use, actually I don't want quizzes to grade, what am I talking about? But seriously, I need your quiz.
Well, we could grade our quizzes for you.
What is,
We wouldn't be biased at all.
is this a gift for me or something? Like, what's this? Anybody know? All right. Well, that's interesting. Sorry, I seem to have asked you a quiz on problems that I like literally solved in class. Daniel pointed this out to me. If I'd sent Daniel the quiz first and then he'd been like, you put these problems in class, and I'd be like, whew, I'll fix it. But I made the mistake of announcing it to you guys first before even telling Daniel, despite his harassing me for the thing early. And well, you should be glad that I have the ethics to not give my son it earlier, because it benefited you all with a stupidly easy quiz. So anyway, I hope you got it right, because I don't mean to be belittling with this comment. I really do have high expectations that you guys can at least repeat arguments I've already said to you, but that's usually the case. So get this cleaned off here. So let me begin with a word of prayer. Dear Father, I thank you for this day again. I thank you for these students, and just ask you to just bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So today, so no one's going to admit to this being their lunch bag? No? All right. Wonder? Pizza? Oh, half-eaten pizza. No. No. No good. Oh, I guess I should take attendance, huh? Let's see here. Here you go. See, Violet's already attended. I'm going to have to take points off her. Anyway, all right, so let us begin here. So today I'm talking about restriction and isomorphism, mostly about isomorphism. So, all right, so let's start with restriction. If you have T is, a linear map from V to W, all right, and U is a subspace of V, then T restricted to U is a function from U to W defined by T restricted to U of X is just equal to T of X for all X and U. All right, so, and this is called the restriction of T to U, all right? It's fairly obvious, I mean, I won't even prove it, that the restriction of T to U is a linear transformation from U to W, right? Well, I'm going to close the door. You guys tell me the proof of that. What happens? You put Cx plus y into it, what happens? You get T of Cx plus y, which is what? Yeah, Ct of x plus T of y, which is T restricted to U of x times C plus T restricted to U of y, thus proving additivity. So the restriction of a linear transformation is necessarily linear, right? You can also talk about an extension. What would an extension of a linear transformation be? I won't write it out on the board, I'll just say it in words, but if you had a linear transformation where if you take, an extension just means like the extension, if you restricted it, you'd get back to what you started with. So it's the opposite idea. I'll show you some extension theorems here to be a little bit more, less vague about this idea here. And so one of the main extension theorems we have concerns this. This is really the main. This theorem I'm about to write does some really nice heavy lifting for us. So if you use this wisely, you can save yourself a lot of trouble and a lot of problems. So here it is. Suppose beta and let's see here. We're going to keep it finite dimensional here, if that's okay with you guys. Beta equals to v1, v2, vn is basis for v over the field f, okay? And suppose W is a vector space over the same field. All right. Right. Furthermore, and I cannot write today. Goodness gracious. Furthermore, suppose L is a mapping from the basis to W, right? So L is a function. And all that means what? That it is single valued, right? Each thing in the basis, it maps to one vector in W, all right? That's what I mean by function, all right? Then here's the punchline. There exists a unique linear extension, let's call it L tilde, which goes from V to W. And if we take L tilde and we restrict it to the basis, we get L. That's what an extension is. An extension is a map whose restriction takes you back to the map you're extending. Let me put this into plain words for you. If we say what a linear transformation does on the basis, then we have said what it does everywhere. We can define a linear transformation by its action on a basis. Before I prove this theorem, let me show you an example of this. So, suppose you're given L of 1 equals to x squared minus x. L of x is equal to x squared, and L of x squared is equal to 1. So notice that 1x squared is basis for P2, right? So there is a unique linear extension of L to the whole of the polynomial space, and here it is, L tilde of, let's say, a plus bx plus cx squared is equal to, well, a times L tilde of 1 plus b times L tilde of x plus c times L tilde of x squared. But I don't know what L tilde is yet. I'm trying to kind of define that. So simple enough. Actually, what you do is, let me just erase the tildes here. That's actually how we do this, all right? Because I'm already given what's the value of L of 1, L of x squared, right? So, all right. This is a times x squared minus x plus b times x squared plus c times, well, 1. There you go. That is the formula for the unique linear extension of L to the whole polynomial space. Now, as we go on, I don't tend to even use the tilde. I'll just say define L on the basis and extend linearly. Right? I'll be like, suppose L is given on the basis as such, extend linearly. I don't technically even need to write the formula down for L, because there is a unique formula which is prescribed from the linear extension, which says impose linearity and, you know, let L map on the basis as is prescribed. That's the linear extension theorem. Right? Yeah?
What is the difference here between L tilde and L?
L tilde has the dimension, excuse me, the domain of L tilde is P2. The domain of L as it's given is just the monomial basis, 1x squared. Of 3 of many. I'm sorry. I regret that. Let's see here. No one cares about that. So where are we? I guess I should prove this, right? The proof is essentially the calculation in example 1, though. All right? So like, you know, so you're given that you've got a linear transformation. I called it L on beta, right? To W. This, and we're supposing beta for the sake of specificity is that, right? And we can let L of VI equal to WI, right? Just call this, just name calling, all right? So if, you know, X, an element of V, has X is equal to the sum I equals 1 to n of Ci Vi, then construct L of X equal to the sum I equals 1 to n of Ci Wi. Oh well. So notice, I mean, this is what I did in example 1, right? This is what I did. And okay, Sam, your question was good, and I owe you one more erasure here. Right? Oh no, I can't remember my own notation. Stand by it. That's the extension, right? Okay, so in my current notation. So this is, oh, by that same token, I'm defining the extension, right? My claim then, L tilde is a mapping from V to W, and L tilde is an element of the linear transformations from V to W, okay? So, all right, let's prove the linearity. If we have X is above and Y are in V, and you know we have X is above and we have Y, let's say with coefficients B, right? Then what is Cx plus Y? I'm going to trade that C for an alpha because I've already used the C sub i's. Okay, that's okay? Alpha. Then this is, notice, the sum over alpha Ci plus Bi times Vi. Right? Could you guys catch up with me? Do you agree? So what I'm saying is that if I take a vector and another vector and I expand them with respect to the basis, then the coordinates really with respect to the basis, it just adds and scalar multiplies likewise, right? Because you know, well, anyway, let me continue on here. So what is L tilde of alpha x plus y equal to then? So you see the definition is if you feed it, I should probably use a different letter than x up here to help you guys see it better, but this right here, let me call this, for the sake of like seeing this better, let's call this like C bar, all right? C bar, and I'll call this x bar just to be weird. Bar. All right, so think about all of this as x bar, right? So the coordinate of x bar is c bar. Well, this is my c bar, right? C bar I. So the definition says I put the sum I equals 1 to n of c bar I times my wi. That's the definition of the extension. I just keep the scalars and I convert the input to the output of the basis on the basis. And then, but this is, of course, the sum over I of, I'll pull the alpha out, I'll pull the ci here, vi, and sorry, my handwriting is, it's not great today. So, that's just a calculation, but what is that? Well, that's alpha. L tilde of what? Plus L tilde of what?
X and Y.
X and Y, right. Because that's X and that's Y by assumption. And so we have proved that L tilde, the extension, is linear, right? So if you impose this formula is what drives the extension, right? Which is just map the basis where it goes and pull the linear combination out. That makes the extension linear. Why is it unique?
Because it holds for all I guess.
Holds for all I. How about this? I mean, there's a formula for it. There's proof by formula. I think formula proves uniqueness, honestly, but yeah.
Yeah. I mean, it's basically because the basis is linearly independent, so there's only one way to construct.
Very good. Yes, it does rest on the uniqueness of the coordinates, which itself rests on the fact that there's only one coordinate for each vector given a basis, right? And that is because we have equating coefficients, right? The whole logical basis for picking coordinates is linear independence of the basis, which, like the equating coefficients, right? Our ability to, so we do all the time, like over, you know, in problems, right? If I asked what's the coordinates of this a plus bx plus cx squared with respect to that basis, you should tell me a, b, c, right? There's no ambiguity there because we can equate coefficients if the vectors are linearly independent. If you're not satisfied with that, suppose you had another extension, right? And then you could show that they're equal on inputs, right? If they both restrict, if you had another thing that also restricts to L, you could prove that it's got the same action as this L tilde I just constructed. That you could complete the proof that way. Anyway, I think I've spent enough time on this already. So this is the unique linear extension theorem, right? So what this means is if I tell you guys how a map acts on the basis, and I say extend linearly, that suffices to define the map, which is sometimes very nice, a very nice way to define a linear map, because I don't have to define it on an arbitrary input. I can divide and conquer, right? I can say, oh, you know, it does this to 1, it does that to x, it does that to x squared, right? Which is kind of nice, maybe. All right, so next up, what did we learn last time? Do you guys remember? So I actually have, if you look at the bottom of page 92, I flesh out what I just was talking through. I take two ones and I show that they have to be the same, all right? So the next up is a definition. And I believe this linear extension theorem extends to infinite dimensions, but I haven't thought about it too much. If you find something awry there, let me know, okay? Because that's one of my, sort of boilerplate goals for my current set of notes is to try to, wherever we can, extend things to infinite dimensional context, like we try to say it, if it's not too much work. And I suspect it's not too much work to extend this current discussion from the finite basis to like an infinite basis. But anyway, so definition 3.24, this is one of the more important definitions in the course. Here it is. Vector spaces. In some sense, it's very boring what happens here. But anyway, here it is. Vector spaces VF over F and W over F. So two vector spaces over the same field, all right, are isomorphic. Isomorphic if there exists an invertible linear transformation let's say psi from V to W. Furthermore, an invertible linear transformation is called an isomorphism. And we write V equals to, not equals, but this like equals to the approximate W if such a psi exists, okay? Question? So let me rehash what we talked about last class. So like last class we learned if you have a injective linear transformation, right? What did we learn last class? Like in summary, we learned, let me just recap, yeah? We learned that if T is injective, then T of linearly independent is linearly independent, right? Schematically, like it maps a linearly independent set to a linearly independent set, right? And we also saw the result that if T is surjective, then T of a spanning set is a spanning set. In other words, or you could say an onto map maps generating sets to generating sets. Now, I proved the first one. I didn't prove the second one, but the proof is in the notes, and it's pretty easy. So what is it? What's the if the linear transformation is invertible? Is it surjective? Is it injective? What can you say? It's both, right? So that means that an isomorphism preserves what? Both linear independence and spanning. So that gives us the theorem that if psi, from V to W is isomorphism, then if beta is basis for V, then psi of beta is basis for W. In other words, an isomorphism has to map a basis to a basis. All right. And then that brings us to the next theorem, which is what I said. In some sense, this makes it kind of boring, but here it is, theorem. V is isomorphic to W if and only if the dimension of V equals to the dimension of W. So two vector spaces are isomorphic if and only if they have the same dimension. And we do mean for this to include infinite dimensional cases. So like these theorems are still true for functions on infinite dimensional spaces. But on infinite dimensional space, we understand this equality in terms of cardinality. Yeah.
Is that because of the linear, or well, is that because of the basis being, because the basis has to be isomorphic, or the isomorphism?
Yeah.
I'm not saying this right, but I'm trying to.
Let's think through it. But I think you're in the right direction. Let's let's try to flesh that out just a little bit. So if V is isomorphic to W, this, right? That means that you've got psi, which is a mapping from V to W, right? And if beta is a basis for V, we've got psi of beta is, basis for W, right? But the cardinality of basis beta is the dimension of V, and the cardinality of a basis for W is the dimension for W, right? And we proved that the dimension is well defined. In other words, that if you have any two bases for a given vector space, they have the same cardinality. This we proved. Or at least I put things on a projector screen and I waved my hands enough to make it true. One of those things happened. But how do I know then that the dimension of V and the dimension of W are the same? What is psi? It is a invertible linear map. It is a bijection. It is a one-to-one and onto map, which does what? That's the whole basis of cardinality, is two sets have the same cardinality if what? If there is a bijection between them, right? That's essentially the definition that we start with. And so, yeah, they have to be equal because psi is a bijection. And we can take the basis one, the basis the other. And then the other direction, if we assume that they have the same cardinality, right? That means that there exists a bijection from one basis to the other. And to create an isomorphism, you simply extend linearly. That's it. Yeah.
So the fact that theorem holds for infinite cases means that extension does hold for infinite cases.
Yeah, I think so. Apparently. I need it, don't I? It must be true then. The question then is, what would be required to extend my proof from the finite dimensional proof that I gave to the infinite dimensional? Like what would be involved in that? Let's think about it for a second. If instead of W, if V and W are both infinite dimensional, right? What that means for something to be a basis is that any vector in the space can be obtained by a finite linear combination, right? That's the definition. So it has to be like we don't have infinite sums. There's no convergence. And so essentially we can make the same definition. See, because if you pick any x and v, even if it's infinite dimensional, it's still the case that there exists a unique finite linear combination of the basis which makes it so. Right? We still have uniqueness of coordinates in the infinite dimensional case. So that is still uniquely prescribed in the same way, because it's just that I can't just go from 1 to n. I mean, well, there's a different choice of I have infinitely many v sub i's to pick from, right? But there exists some finite subset of them which gives me this. And likewise, when I pick the y, so like this I'd have to use one finite subset of the basis to get the x, a different finite subset of the basis to get the y. But when I put those together, I still have a finite linear combination of the infinitely many basis vectors that exist in the basis for v. And I can still go through the calculation in the same way. It's just I can't make all the sums from 1 to n. I have to fuss about how do we obtain vectors from a finite sum of vectors in the infinite basis. But I think otherwise the calculation goes through pretty much the same. So I should have just stated with authority, this proof naturally generalizes to infinite dimensions, and I wouldn't have been wrong. Although I guess naturally depends on how you feel about the infinite dimensional part of this course. But
So is the infinite basis just the same among all examples because it contains all?
oh no, the infinite basis for different examples is different. Like the infinite basis for the real, okay, so like let's talk about this. Not all infinite vector spaces are the same. They are different. They're very different.
Okay, well, I mean, if we're talking about like the reals in two different cases with an infinite basis in both of those cases.
Oh, reals, okay, but hold on. Reals as what? You say reals with the infinite, as a field. Well, I mean, but reals, how about this? Reals is a vector space. What's the field? You have choices. See, we can either talk about the real numbers as a vector space over R, or we can talk about the real numbers as a vector space over Q. Those are really different things.
Okay.
See, because like over R, the reals are just one-dimensional. It's kind of silly.
Yeah.
Because any real number, if I have x in the reals, right, then x is equal to like x times 1. So it's in the span of 1. On the other hand, so here I'm talking about v equals to r with the field being r. In contrast, if I talk about v equal to r with the field being rational numbers, I can't even write down for you how to build that real number as a sum of rational numbers. But we can prove that it's possible. Because it is easy to prove. I mean, it's simple to prove this is a vector space, right? Like, if I take the sum of two real numbers, it's a real number. And if I take two rational numbers, a and b, right? And I multiply them by a real number, I get, and you can sort through it. All of the axioms for the vector space still work with just taking the rational scalars, right? But what's the basis? How would you write x as, like a sum over ci ri, where ri is an element of Q? And also, well, I guess r doesn't have to be, excuse me, my bad. This is an element of R, but Ci is an element of Q. So the constants in Q, like x is in a rational span, span over the rationals with respect to some basis. How do I know the basis exists? We proved that a basis exists for any vector space using Zorn's lemma and the axiom of choice, which is non-constructive. In other words, like, just because it exists doesn't mean I can write it down. And this is where that push comes to shove. I mean, like, I cannot write down the basis here, but you can prove that it has to be infinite dimensional. It can't be finite dimensional. The bonus problem at the end of your quiz, I think, is kind of about that. I don't know how to solve that, right? I have to think about that. I'm not sure I can solve it. You guys will figure it out. But there is a hint and stuff. But anyway, my point to you is that the dimension, the rational dimension of the reals, right, is infinite.
Yeah.
But I also wanted to say, like, I gave you an example of rational functions on the reals, right? And I showed you guys there that on the one hand we have the monomial basis, right? Because any polynomial is a rational function, but we also have like the basic rational functions of the form 1 over x minus alpha, or that to a power, and also the things like ax plus b over x minus alpha squared plus beta squared, right? The irreducible quadratics to a power. And the partial fractions decomposition has either this, or also polynomial. How many of these does it take? Well, there's a countable number of these. These, on the other hand, have a real parameter. So the cardinality of all these, if you take the collection of all these, we're talking about the continuum. So what that means is that the dimension of I don't have a notation for it, but a usual notation for it is this. Rational functions on x is like this. In contrast, so this is, I would say, aleph 1. The dimension of the continuum. On the other hand, the dimension of the polynomials, because it has the monomial basis, which is countable, is just aleph naught. Those are both infinite dimensional vector spaces, but they're not isomorphic. They can't be because the bases have different cardinality. And if there was an isomorphism, it would say that the cardinality of both bases had to be the same because the isomorphism is a bijection.
Okay, yeah.
I hope this helps. I mean,
It did.
good. This is weird. This is weird stuff. Like, blows my mind. This part. That part, okay, but this part, weird. It bothers me because I can't write down the beta. I can't write down the basis. I mean, I know it's there, but how do you write it down? So, Zorn's lemma is weird. What can I tell you? But you guys all believe in choice. So, wait a minute. No, that's not right. It's not right. No, it's not. It's not right. Powers of 10? Oh. Aha. Right. Anything can be written as a sum of powers of 10. What's the trouble? No. Powers of 10, I think you could prove powers of 10 are, well, maybe they're not linearly dependent. They might be rationally dependent. Yeah, 1/10 and 1/100th are dependent as rational, in rational vector space, like those are the same. You know what I'm saying? Like 1/10 and 1/100th, since 1/100th is 1/10 times 110, that's linearly dependent over the rationals. But there's something right about what you're saying, because you're thinking any real number can be expressed as a sum of powers of 10, but that's an infinite sum. And we're not allowed to take infinite sums. We have to take, everything has to be built from a finite sum for a basis. It's finite linear combinations that we deal with in here. Yeah. All right. So, question then. Well, there's a couple things I should say. One thing I should say is that isomorphism provides an equivalence relation on the set of all vector spaces, right? Any two vector spaces, so a vector space is isomorphic to itself under the identity map. The identity map is an isomorphism from the vector space back to itself, so that proves reflexivity of the equivalence relation. If psi is an isomorphism from W to V, or excuse me, from V to W, then psi inverse is an isomorphism in the other way. So that gives you the symmetry of the equivalence relation, right? Isomorphism of V to W means that V is isomorphic to W as well. Other way around, W is isomorphic to V. And then transitivity follows because if I have U is isomorphic to V, and if I have V is isomorphic to W, if I have an isomorphism from U to V, and if I have an isomorphism from V to W, the composition of those linear maps is linear, and the composition of bijections is a bijection, as you will prove in my Math 200 class next semester. Maybe not you guys. Maybe one of you. Maybe two. You're going to come back and take 200? Dang it. All right. Oh well. So wait, why do I want that? Anyway. So all right. So be careful. I think about FERPA. FERPA. Anyway. So. My point is that the composition of isomorphisms is an isomorphism, so that means that U is also isomorphic to W, which shows you that we have transitivity, right? So, and it's really easy to label the equivalence classes. What are all the vector spaces which are equivalent to one another? What joins them? You just calculate their dimension. So once we have to pick a common field for this discussion, right? There's no discussing isomorphism of like how it relates to rational spaces versus real spaces. Like you could, but that's a much harder thing to sort through. So let's see here. Another comment I should make. If we have V over F with basis beta, then if we define phi sub beta of x to equal to x beta. All right, where that's the coordinate vector of x we defined before, right? Now I'll keep it finite dimensional here. We'll suppose that the dimension of v over f is just n, right? If that's the case, this has to be an element of what? Like Fn, right? And is it a linear transformation? Well, yeah. You know, like it's definitely the case that, and we just actually worked this out in our previous proof, didn't we? I mean, this essentially the proof of this was in the proof I just erased. If you really look at it, it's right there. It's just that calculation we did. See, the coordinates of a linear combination is the linear combination of the coordinates. But that means that the coordinate map, phi beta, is linear transformation. Right? So phi beta is an element of the linear transformations from V to Fn. So let me show you how I used to prove, you know, and this is often how Dr. Skambordis would prove that two vector spaces are isomorphic. I mean, in just a finite dimensional context, there's a very simple way. So here's how you do it. If I've got V, right, and, you know, we're talking about dimension of V equal to n, and I've got W, dimension of W equal to n. So I've got a basis over here beta. I've got a basis over here gamma. Well, I can simply map phi beta down here, and can I map phi gamma down here? Down where? Well, Fn. And of course I could even combine the picture, right? I could have had them mapped to the same copy of Fn if I wanted to. I separated them. It'll serve us well in the future. So, I mean, fine, I'll just, down here, I'll put the identity on. The identity map on Fn, right? That's a way to get from there to there. So what's the isomorphism up top? Can you guys tell me? How do I get an isomorphism from here to here? Yep.
Compose those three phis.
Compose the three phis. Yeah. So we'll write psi is equal to, I got to go, let's see here. To get from here to here, I got to go this way. So I can do phi, so the last shall be first, right? In composition, so if this one comes first, it has to go last. So I do phi beta first, right? That takes me from here down to here. I compose with the identity, which I'll write just to be dumb. Right, that takes me over to here. And then I got to go back up. So I go the opposite way, right? So this way is phi gamma inverse. Let me write that a little bit bigger. So psi rather is the inverse of the gamma coordinate map composed with the beta coordinate map. And that is the composition of linear bijections and is therefore a linear bijection, proving that V and W are isomorphic. This also gives you a roadmap on how you could construct an isomorphism from one vector space to another. If you know coordinate maps for both vector spaces, you can construct the isomorphism using this guide. I don't really recommend that. I recommend writing isomorphisms down by like art. Like just common sense, basically. Let me show you some. Like how do we find an isomorphism between vector spaces? What do you guys think? Well, first of all, they better have the same dimension, right? Otherwise we're kind of in trouble, right? So here, let me make up some examples. What example am I on? 2, 3? 3 maybe? 2? I'll take 2. So how about this? What about the isomorphism? If I want to find an isomorphism from, say, V equals to C2 and W equals to R4. So I'm going to actually ignore that and just write down the formula, because writing down the formula is actually how I do things. Yeah. I don't think, I mean, this is theoretically interesting, but pragmatically it's not usually necessary. So what you need to do is just write down what is something, so of course, so for this to be isomorphic, what am I talking about? What's my field here for both? R. All right, so I'm thinking about complex 2 space as a real vector space. All right? So my complex 2 vector looks something like, you know, x1 plus iy1, x2 plus iy2, right? That's a typical complex 2 vector. What's the corresponding 4 vector?
x1, y1, x2, y2.
Yep. Now, somebody else here was like, no, you're wrong. It was x1, x2, y1, y2, right? Here's another flavor option. How many options are there? How many different isomorphisms are there from one vector space to another? What's that?
Yes.
Yes. So if we're working over a field with characteristic 0, like the reals or the rationals, the answer is infinitely many. There are infinitely many, as it turns out. Do you want me to show you that? Suppose psi is an isomorphism from V to W, right? So how can you find another isomorphism from V to W?
I guess using using what that whole diagram is saying is
Mm-hmm.
to find the inverse 5 gamma, you compose it with the 5 beta.
Oh, okay. So like just. Oh, right. Well then.
Could that produce? I guess you have to find the bases and then.
Okay. Yeah. Great. That's exactly the point. Yeah. Thank you. So I was trying to do something related to this one, but I don't need to do that. So thank you. Let me call this a different letter altogether to like make it more divorced. So let me use this thing. I never use this thing. Whatever this is called. So that one. So there's an isomorphism. I broke Ellie. If we use the psi that, like you just said, you know, the gamma inverse map composed with the beta map, that's an isomorphism from V to W given a basis beta for V and a basis gamma for W. How many choices are there for beta and gamma? Yeah. Right. There's as many choices as there are many invertible matrices over the field that you're working. So there can be a finite number of bases if we're working over like a finite field. If you're working over a vector space like over say Z3, you could have the situation where there is actually a finite number of bases. But outside that context, if we're working over the reals or the complexes or the rationals, there's infinitely many bases to pick from. But yeah, there you go. That's an isomorphism. How about this? I want to find an isomorphism. Suppose I want to go from R2 by 2 to, I don't know, third order polynomials. Now, this is very dangerous because I'm going to end up doing your homework because I'm just making these up off the top of my head, which is also how I made up your homework, which is why they have the same problems, right? So, my bad. So you're okay with that? Yeah. Is that your lunch bag?
Yes, sir. Oh, no, not mine.
Rats. That's right. Somebody left the phone in my last class. His name was Benjamin. I don't know his passcode though. So here's a typical 2 by 2 matrix. What's the isomorphism? I mean, you got infinite many choices, but there's one choice that's right. And the choice that's right is a plus bx plus cx squared plus dx cubed. Yay, we're done. I want to map example 4. Suppose I want an isomorphism from, say, nth order polynomials over the reals, Cartesian product with Rn, to polynomials of order what? 2n plus 1 over the reals. Find an isomorphism. I should be able to do it because the dimension of the Cartesian product of two vector spaces is the sum of the dimensions of the vector spaces that have been Cartesian product. Plus 1. See, this has dimension n plus 1. And this has dimension n, so 2n plus 1 is the dimension. And so if I can use this for my isomorphism symbol, I'm looking to, map a sum, right? I equals 1 to n of, like, let's say let's say I equals 0 to n. How about that? Of ci x to the power I, comma, v, right? J equals 1 to n of, the Vj, Ej, I guess we could say, yeah. So what do you want to do? Here's what I'd do. I would say, let me just call this thing f of x, right? Let me call this thing v. So my formula is just going to be f of x plus the sum j equals n plus 1 to whale. 2n plus 1, I suppose. No, just 2n, right? Just 2n. Oh, this better be whatever n plus 1. It better be n plus 1. If this one goes from 1 to n, this j better range from 1 to, I think it's 2n plus 1. We'll think through it in a second here. But I can just use, oh man, I'm sorry guys. Let me stick with the j equals 1 to n. It's messing with my formula. Sorry guys. J equals 1 to n of the Vj. I want the numbers here. And I want to move it over to the part of the polynomials I haven't used yet, right? Like this goes from the constant terms up to the power n. So what's past that? It's like n plus 1, right? So I should do x to the n plus j maybe? Is that right? Does that work? Oh. You guys told me 2n. You were right. It was 2n. I counted the one over here. I talked you out of it. I bullied you out of it, right? But my comment equally well applies over here. What's the dimension of this? 2n plus 2. Yeah. So I should have 2n here, as I'm starting to experience in my formula. Now we're okay. You can prove this is a bijection, right? If you set phi of something equal to phi of something else, you can get equality of all of the coefficients because when you look at the monomials ranging from constants up to x to the power 2n, they're all linearly independent, and it forces equality of the coefficients, which then forces the equality of the inputs. So it's 1-to-1. And the fact that it's surjective is kind of obvious as well. But anyway, my point to you is you can write down isomorphisms, just be creative, think about it. Like, don't try to do it. Check yourself once you do it, You're like, this isn't really a technique you're teaching. No, I would say this is more of an art. Now, if you get stuck, you can always fall back on the tried and true. And I have a list of like 10 examples in the notes. So I hope that's enough for you guys to figure out how to write the isomorphism in the homework. I think it is. Now, this idea that the coordinate map is an isomorphism is an important idea. We will be working a lot more with that. Like, I think next time we look at what's called the matrix of a linear transformation. But now it's the matrix of an abstract linear transformation. So we can't just calculate the standard basis. We have to calculate the basis with respect to, the bases which are given. And we'll see that it's similar to what we did before, but on the other hand, exciting and new. So it's all good. Anyway, thanks, guys. I think I'm out of time. Oh, my goodness.